Hello and welcome to BSci Lab Number 1. BSci, that's Building Scalable Cisco Internetworks. Here in BSci Lab Number 1, we're going to be taking a look at EIGRP, Cisco's very own Enhanced Interior Gateway Routing Protocol. EIGRP, we consider that to be an advanced distance vector routing protocol. Let's take a look at some of the objectives we have for this lab. First of all, we want to see how to perform basic EIGRP configuration, enabling the EIGRP process on a router, going in and adding network addresses to be part of that EIGRP process, forming neighborships. Then, after we have basic EIGRP configured, we're going to have an issue. We're going to have an issue that deals with auto summarization, and we'll show you how to go in and, as a best practice, turn off the auto summarization feature. We can also load balance our traffic across multiple paths. We might have an Ethernet link and a serial link and send packets over both links. And while many routing protocols can load balance across equal cost links, EIGRP can do it across unequal cost links. Next, we want to take a look at how to specify a default route, maybe pointing out to the internet. We want to point out to the internet to reach the rest of the world, and we want to advertise that default route information to the other routers in our topology, and then we'll wrap it up with a few show commands to verify or possibly troubleshoot our EIGRP configuration. Here's the topology we're working with. We have 3 routers. Notice we have Ethernet networks hanging off of routers R1 and R3, and also pay attention to the fact that we have dual links. We have an Ethernet link between routers R1 and R2, as well as a serial link, and a single serial link between routers R2 and R3. Also notice that we're using 24-bit subnet masking everywhere, and we have a subnet of the 10-dot network on router R1. Let's see how to set up EIGRP on our routers. First of all, in global configuration mode, we get into router configuration mode by saying router EIGRP and giving an autonomous system number. That enables EIGRP on the router. It specifies what this autonomous system number is, and that number has to match our neighbor. Then we can start adding a series of network commands. Network, followed by the address of the network, followed by not a subnet mask, but a wildcard mask. That is going to specify the networks that our router knows how to get to. Maybe they're attached, maybe we've statically configured them. We're going to be advertising those networks out to the rest of the world. That's how we enable EIGRP and add networks. Let's actually do this on our routers. Starting off over on router R1, let's go into global configuration mode and say router EIGRP, and let's use some context-sensitive help to see what range of autonomous system numbers we can specify. Let's just use 1. Now that we're in router configuration mode, we can give a series of network commands to say what networks we wish to advertise via EIGRP. First up, let's say network 10.1.1.0. And this is a 24-bit subnet mask, meaning that our wildcard mask is going to be 0.0.0.255. Let's add another network statement. This time it's going to be network 192.168.1.0, again with that 24-bit subnet mask, translating into a 0.0.0.255 wildcard mask, and our final network is 192.168.11.0. I think we're done on router R1 as far as setting up basic EIGRP. At this point, why don't we move over to router R2 and set up a similar configuration. Let's get into privileged mode on router R2. And from global configuration mode, we enter the command router EIGRP1. Notice the autonomous system number matches our neighbor. And here we again give a series of network statements. We say network 192.168.1.0, and we still have that same wildcard mask of 0.0.0.255. Notice after we gave that first network statement, we got some feedback to the console. It says that we had a neighbor change. The dual algorithm, EIGRP's diffusing update algorithm, has formed a neighborship. That's great news. Our next network statement, 192.168.11.0, and again we get a neighbor change statement. We formed a neighborship across the serial link between routers R1 and R2, and we've got one more network to educate EIGRP about, and that is network 192.168.2.0. Finally, we need to move over to router R3. Over on router R3, we need to configure just a couple of network statements. Let's get moved over to router R3, get into global configuration mode, enable EIGRP again with an autonomous system number of 1, and the first network statement is going to be network 192.168.2.0 with that 24-bit wildcard mask. Our next network statement is going to be network 10.1.2.0 with a wildcard mask of 0.0.0.255. Again, we get a neighbor change statement indicating that we have formed a neighborship. What have we done so far? We have configured EIGRP on each of our routers. However, I'm concerned that we may have an issue. Let's do this. Let's go over to router R2 sitting in the middle and take a look at our IP routing table. As we take a look at the IP routing table, notice that we don't have specific network information for our two different subnetworks using the 10.0.0.0 address space. Instead, we have summary information. We've learned about a 10.0.0.0 network with an 8-bit subnet mask. I don't think that matches up with what we actually have, though. We've got a couple of 24-bit sub-networks out there. As a result, it says all traffic going to the 10. network is going to go out Ethernet 0. I think we're going to have issues reaching that subnetwork off of R3. Let's try something. Let's do a ping just to verify that we cannot reach that 10. network off of router R3. We tried to ping 10.1.2.3, no success. The network is unreachable. Let's investigate why that is. Why would that network be unreachable? Let's go back and see our topology, and I think we can see what's happening here. Auto summarization is turned on by default. EIGRP, by its very nature, is going to summarize networks at their classful boundary. The 10. network is a Class A network. Therefore, when router R1 sends its routing update over to router R2, it's not going to tell it about the 10.1.1.0 network with a 24-bit mask. It's going to tell it about the 10.0.0.0 network with an 8-bit mask. That's also what router R3 says, and router R2 says, oh, two different ways to get to the same network? I'm using the one over the Ethernet link, because by far that has the best metric. How do we fix this? We need to turn off auto summarization. To turn off auto summarization in router configuration mode, we want to say no auto-summary to disable automatic network summarization. Let's do this for each of our three routers. Let's start back over on router R1. Let's go to router R1 and get into router configuration mode. For our EIGRP process, we say router EIGRP1, and we say no auto-summary. Now, instead of advertising an 8-bit mask, it's going to be advertising the actual 10.1.1.0 network with a 24-bit mask. Let's do the same thing for router R2. We say no auto-summary in router configuration mode. And finally, on router R3, we do the same thing. Let's get over to router R3 in router configuration mode. We want to turn off auto summarization with the command no auto-summary. I think this is going to fix our issue. Let's go back over to router R2 and verify that we now have specific route information for these two different 10. network subnets. If I do a show IP route from R2, Let's see what we have. Look at this. We now know specific network information about the 10.1.2.0 network with a 24-bit mask and the 10.1.1.0 network with a 24-bit mask. One is accessible out of interface serial 1. One is accessible out of Ethernet 0. Do you think our ping will work now? I suspect it will. Look at this. We can now successfully ping the Ethernet interface on router R3 thanks to turning off auto summarization. Something else we might want to do, take a look at the dual links between R1 and R2. Wouldn't it be great if we could somehow load balance across those links, send packets across both the Ethernet as well as the serial link? We can do that using a feature called variance that EIGRP offers us. With variance, we can say, even though the metric is better on one link, if the metric of the other link varies by a certain factor, we will send packets across that link as well. Here's how we set it up. In router configuration mode, we say variance and then give this multiplier. The multiplier says, how many times worse can a metric be on another link and still load balance across that link? As an example, just to make the math easy, let's say that the metric to cross one link was a metric of a 10 and the metric to cross another link was a metric of a 20. But let's say that we specified a variance of 3. If we multiply 3 by the metric of the best link, 10 times 3, that's 30. The metric of our other link is 20. That's less than 30. As a result, we could load balance across both links. In our case, we want to set up variance on routers R1 and R2. Let's start off on router R2. Let's say router EIGRP1 to get into router configuration mode and say variance, and we can have a wide range of variances. Let's say variance 10. The metric of our backup path can be about 10 times worse as the metric of our primary path. Let's give the same command over on router R1. We get back into router configuration mode on router R1, and we say variance 10. Now, let's take a look at our routing table. Let's see how router R1 knows to get out to the rest of the world. Look at this. To get to, for example, the 10.1.2.0 network, we have two different paths that we're going to be load balancing across. Now notice the metrics are quite different. The metric for the fast Ethernet interface is noticeably better than the metric for the serial 0/0 interface, but because it's not more than 10 times worse, the serial interface is not more than 10 times the metric of the fast Ethernet interface, it's going to be usable in this load balancing scenario. Next up, let's take a look at how we can point out to the rest of the world. Let's see how on R3, for example, we could point out to a default network. Maybe this points out to the internet. Let's go into router R3, set up a static default route, and then advertise that default route to the rest of the topology, R1 and R2. Here's the command we can use, IP route 0.0.0.0 space 0.0.0.0, that's pointing to a default route, and then we can give either the interface ID out of which we will send packets going to that default network, or specify the next hop IP address. Let's go out and set this up. We begin over on router R3. On router R3, in global configuration mode, let's statically configure a default route using the syntax that we just saw. We get moved over to router R3, get back into global configuration mode and say IP route 0.0.0.0 space 0.0.0.0, and let's specify an interface of Ethernet 0. That's the way we get out to the rest of the world, we'll say. Then back in router configuration mode for EIGRP, let's advertise that default route. Let's say network 0.0.0.0. Let's just verify that this default network is appearing in our routing table. We'll do a show IP route and see that we have a statically configured route with a star next to it, indicating that that is a candidate default route. And to get to that default network, we simply send packets out of Ethernet 0. Let's make sure that this information was propagated to the remainder of the topology, however. On router R2, if we do a show IP route, great news, we have a default route from the perspective of router R2 that points over to R3 out of interface serial 1. What about router R1? Let's verify that the information made it there as well. Let's get moved over to router R1 and give a show IP route command. Scroll down just a bit more. There it is. We have a default route, and thanks to our variance configuration, we can reach that default route over either serial 0/0 or fast Ethernet 0/1. At this point, I think we've completed our configuration. Let's give a couple of show commands on router R2 to do some verification. Let's do a show IP EIGRP neighbor command. On R2, you recall that we have 3 links that connect us to our neighbors. Out of Ethernet 0, serial 0, and serial 1, we see the IP addresses of our neighbors as well. Another great command for verification and troubleshooting is the show IP protocols command. This shows us that the routing protocol in play on our router is EIGRP, and it's for autonomous system number 1. And from a troubleshooting perspective, we need to be aware that neighbors need to share the same K values. If you remember in your EIGRP studies, the K values determine what components are used in calculating EIGRP's metric. With default K value settings, we're only going to be considering bandwidth and delay. And there's a lot of controversy about whether or not MTU is really used. Let me give you the scoop on MTU. You might have heard that EIGRP can make its metric calculation using bandwidth, delay, reliability, load, and MTU size. If you look at the formula that uses the K values, you'll see that MTU is actually not considered, regardless of our K value settings. It was originally intended to be a tiebreaker, but it was never fully implemented. So technically, we're only going to be considering bandwidth, delay, reliability, and load, depending on how we have those K values set up. What have we accomplished in this lab? In this lab, we started off with a basic configuration of EIGRP. We took a look at how to enable EIGRP on the router and add networks to the EIGRP routing process. But we had an issue, didn't we? We were auto-summarizing, and that was causing some undesirable results. So we saw how to turn off auto-summarization with the no auto-summary command. We then saw how to load balance across different paths, even if those different paths had different metrics, using the variance feature. We configured a default route to point out to the rest of the world, and we saw how to advertise that route via EIGRP. And then finally, we wrapped up this lab by taking a look at a couple of show commands for troubleshooting and verifying EIGRP.